Hello everyone, this is Miss Berlin and this lecture video is all about the derivation of the six basic equations of projectile motion. And when we say projectile motion, we mean to say that this is the motion of an object that is projected or thrown into the air when after the initial force that launches the object, the air resistance is negligible and the only other force that object experiences is the force of gravity. So for example, we have here the graph, right? We have here the graph. And let's say you are playing a soccer or a football here. Of course, you will be launching an initial velocity. Your kick will experience an initial velocity on that, right? This will be the initial velocity, this one, this line here. And this initial velocity is represented by V sub naught. All right. But then the object that you kick, let's say the ball, will experience a parabolic path upon the projection. So it will experience a curved path upon projection. Alright. Now we call this here the parabolic path as the line of trajectory. Line of trajectory. Alright. And then we call this part here, as you can see, we have an angle here, right? And we call this angle as the angle of projection or angle of projectile denoted by theta. This one, angle of projectile, represented again by theta. This one. Again, this is the y component, this is the x component of the graph. So we will be deriving the six basic equations of projectile motion through this graph and from the previous SUVAT equation, or what we call the three equations of uniform motion, right? And let us derive first the first equation. So we know that the y component of a projectile motion and the x component of this one is independent of each other. You have to take note that the most important concept in projectile motion is that when air resistance is ignored, the horizontal and vertical motions are always independent because they are the object or the particle is only acting because of the force of the gravity without the influence of air resistance. Meaning to say, we will be deriving equations from this x and y component. And on that note, I'll be having first the x component. Here, the x component, or the one that represents the horizontal uh, line here, the horizontal vector. So for the x component and y component as well, we will be deriving six equations, three equations each. So for x component, we will be getting first the acceleration component of the x. So the acceleration is represented by x. Okay, this one, a sub x. I just give an identity to the acceleration so that it can be denoted that this one is an acceleration for the x component here. All right. And when we say acceleration for x component, the acceleration here is push and pull or accelerating and decelerating. It is said to be constant in horizontal motion. So if it is constant, meaning to say there is no change, right? So therefore, the acceleration will be equivalent to zero. This is our first equation. Let us now find the second equation in the horizontal component. So for the second equation, we will have here the following. We will deriving the second equation from the previous equation from the SUVAT equation, which is V sub F is equivalent to AT plus V sub I. Alright? So we will be translating this equation into projectile equation. Alright? We will be substituting the variables with the variables present in the graph and giving this an identity, and we will give this an identity of the x component. So on that note, the V sub f here will become velocity of the x component. Here, this is the x, this is the y, right? Velocity of the x component, which is equivalent to the equation or to the value of acceleration at the x component. Remember that the equation earlier is acceleration at the x component is equals to 0. Mean to say the acceleration at the x component will be equal to 0 multiplied 2 time plus the initial velocity at the x component. So the equivalent variable of initial velocity based on our projectile graph is v naught or v sub o. And then let us give this an identity of the x component. So v naught of x or initial velocity of the x. That is what we mean by that. And the next thing that we need to know is that the v naught of x, we have to find the value of this one because initial velocity of the x, we don't have an initial velocity of the x. We only have the angle theta. So given the presence of the hypotenuse, which represents the distance from the vectors, and also the presence of the degree, we have to use a trigonometric function cosine. So the cosine theta is being used if you want to find the y component, I mean the x component rather, of the vector, right? So the cosine theta is equivalent to adjacent over hypotenuse, right? And the next thing that we need to do is we have to isolate this diagonal here. Isolating that, you have v naught here. And we have to draw the horizontal component of that and the vertical component. But then you can see that we have here a 90-degree angle. That's a right triangle. And then we will have here the degree theta. Alright. And this one here, the side here is the hypotenuse. The opposite side. That is the opposite. And then the side of this angle is the adjacent side or the adjacent leg of this triangle. And we have to name the sides of this triangle, the opposite and adjacent. So this is the V naught, this is the hypotenuse. For this case, the V naught of this one for y is V naught of y. For x, that is V naught of x. Okay? And the adjacent corresponding variable for the adjacent of cosine theta is equivalent to the V naught of x over the hypotenuse of V naught. What we need is the value of the V naught of x. We need to find the value of this one. So we have to eliminate the V naught here. And for us to eliminate that, we have to multiply both sides by V naught. So multiplying both sides by V naught, we will be able to cancel this one, cancel. And you will be left out with the equation V naught cosine theta is equivalent to V naught of x. Therefore, you have now the corresponding value of this V naught of x, the initial velocity of the x. The next thing that we need to do is we have to substitute that, of course. So from here, velocity of the x is equivalent to 0 times multiplied to time, that is cancel, of course, and input the value of the v naught of x. We are inputting that because we don't have earlier the specific value of the velocity or initial velocity of the x here. We only have the initial velocity as we throw the ball, right? But then we don't have for the horizontal component, so we have to identify that. And the corresponding value of the initial velocity of the x is V naught or initial velocity multiplied to cosine theta. This is the second equation. Now for the third equation, we will be deriving the displacement at the x component or displacement at the horizontal. So meaning to say we will be deriving from the Suvat equation from the second derived equation yesterday or on our previous lesson. So you will have here the equation from the Suvat is displacement is equivalent to v sub I multiplied to t plus at squared over 2, right? That is the equation, correct? So for the x component, again, we have to make this a projectile equation by giving an identity of the x component on each of the variables and by replacing the variables as it corresponds to the projectile graph here. So the d here, the displacement will become displacement of x is equivalent to the equivalent variable of initial velocity here. The initial velocity is the v naught, so that is v naught of x multiplied to time plus at squared. The a is equivalent again from the first equation. Acceleration at x is equals to 0. So 0 multiplied to t squared over 2. So the next that we need to do is, of course, we have to input the equivalent value of v not of x again, because again, we don't have the initial velocity for x here. We only have the initial velocity as shown on that angle, but we don't have for the x component. We will be using the earlier v naught of x equals v naught multiplied to cosine theta. This is the earlier derived or earlier value that we get from the cosine theta on the trigonometric function. So on this case, we will be substituting the v naught of x with this one, v naught cosine theta multiplied to time. And then of course, we have to cancel this one, the o or 0 multiplied to time and then over 2, because anything that you multiply or divide by 0 will always have the same answer, which is 0. So cancel that. And we have to arrange this, of course, so to avoid confusion, but then it is already okay or already good for an equation. Anyway, a multiplication has an associative property. So the next thing that we need to do, rearrange. You will have d sub x is equivalent to v naught multiplied to time multiplied to cosine theta. And this is our third equation for the horizontal component. So we already have the first equation, this one, the second one, and then the third one. This is the third one. All right. So we will be finding next the y component. So you will have here y component. That is what we are looking for. So for the y component, the first one that we need to find is the acceleration at the y, a sub y acceleration at y component here, the vertical one. And what is the acceleration at vertical component? Yes, you might say that 9.8 meters per second squared or negative 9.8. So that is equivalent to g, right? This is our fourth equation. The next thing that we need to find is the velocity of the y component. And we will be deriving again from the Suvat equation from the previous derivation yesterday. V sub f, or from the previous discussion, is equivalent to 80 plus initial velocity. So we have to translate this equation from the Suvat into projectile equation. And in order for us to do that, we have to give an identity of y component on this one. At the same time, substituting or translating the variables into based on the graph given here in this projectile graph. So for the v sub f, you will have v of y, velocity at y component is equivalent, of course, to the acceleration at the y component, that is g, multiplied to time here, plus the initial velocity. Okay, the initial velocity is the v naught based from the graph. But we have to give an identity of the y. So that is v naught of y. This is the formula. But then, just like what I have said, for the initial velocity at the y component, to the 180 degrees of that, you don't have an initial velocity yet. You don't have the given value. So you have to find that using the sine theta, using the trigonometric function sine theta. So again, we will be isolating the diagonal, horizontal, vertical, degrees here. This is the opposite side. So this is the opposite side. This is the v naught, the hypotenuse. And this is the adjacent leg of the triangle. So for the v naught, this is v naught of x, right, from earlier. And then v naught of y, or initial velocity at y. This is the v naught of y. This is the one, v naught of y. But then, again, we need to find the exact value for the v naught of y because there are no given value. So, velocity at the y is equivalent to gt plus, of course, what trigonometric function are you going to use? You will be using the sine theta since you are looking for the y component. Sine theta for y component. Remember that. We have discussed this in the vectors. So, sine theta is equivalent to opposite over the hypotenuse. Correct? So, alternating that, we have to erase some parts. The opposite is v naught of y. And then the hypotenuse is v naught. Yes, this one. This is the hypotenuse, the longer leg. V naught. Alright. So, therefore, let me erase this one. Again, sine theta is equivalent to opposite, which is v naught of y, over the hypotenuse, which is v naught. We are just looking for the value of the v naught of y here. So we have to eliminate this v naught. And for us to eliminate this, we have to multiply both sides by v naught here, initial velocity, and cancel, you will be left out with the v naught sine theta is equivalent to v naught of y. So therefore, the value of the v naught of y is this one, v naught sine theta. So this is the fifth equation. This is the fifth equation for the velocity at the y component. Now let me erase this again. So now we will be finding the third equation for the y component, the sixth equation for the projectile motion, and that is displacement. And for us to obtain that, we have to derive from the Subat equation, from the previous equation, and that is displacement is equivalent to initial velocity multiplied to time plus 80 squared over 2, right? And then again, we have to give an identity of y component here. At the same time, we have to change the variables based on the variables on the projectile. We have to translate the variables into the variables depicted in the graph. So let us give an identity on each variable. So d, or displacement at y component, we have to find that, is equivalent to initial velocity. The initial velocity is what? That is v naught. Okay, v naught of y plus, alright, plus, multiplied to time. Here, we have still the time, plus 80, the value of a at vertical component, right? A sub y is equivalent to g. So, g, t squared over 2, right? And then, again, we already have the value of the v naught of y from the previous derivation or from the previous calculation of the sine theta. We said that sine theta is equivalent to, that the v naught of y is equivalent to sine theta multiplied to v naught, right? So, or v naught multiplied to sine theta, that's okay as well. So, on this case, you will be changing the variable or substituting the value of the v naught of y with this value. So, d sub y, or displacement of the y component, is equivalent to v naught multiplied to sine theta multiplied to time plus gt squared over 2. This is the sixth equation, right? So that is all for the derivation of the 6 basic equations of projectile motion.